the approach that I'm going to follow is slightly different from what's presented in the book. Potential can be a tricky concept, a slippery concept. So I would like to make the slippery surface a bit rough so that you can put your feet on it. Now, you've already studied mechanics. Suppose I have a single particle and nothing else in this world, just a particle and perhaps an observer, but nothing else in the world. So this particle will have some energy. What energy would it have? What kind of energy would it have, in other words? So it's just a single particle. Can it have a potential energy? There's nothing else in this world. There's nothing that you can this particle can refer to. It's just empty space. Nothing it can interact with. Will it have any potential energy? No, it cannot have any potential energy. Potential energy can only come through interactions. So an isolated solitary particle on its own with no interactions whatsoever cannot have a potential energy. Potential energy is always with reference to something else. I'm standing on the earth, I'm interacting with the earth. The earth has a gravitational force of attraction exerted on myself, which is generally called the weight. So because of this interaction, I have potential energy. If I were in an area of space where there were no nearby gravitational masses, which is something really almost impossible to have, I cannot ascribe a potential energy to myself. So potential energy only arises because of interactions. This solitary particle that's on its own will only have a kinetic energy. It can be moving. There's no one stopping it from moving, and motion is just like rest. Zero velocity. There's nothing special with zero velocity. You can have a finite velocity. Okay. So the Greeks thought that zero velocity is something special, or a velocity that is non-zero is different from zero velocity. But this particle can be at rest, it can be moving. So this particle can only have kinetic energy. And if you're talking about particles, you can also consider adding the energy of being, which is called the intrinsic rest mass energy of this object. So this is what the energy of the particle can be. Alright? This kinetic energy, of course, you know, if you're in the non-relativistic regime, it's approximately given by half mv squared, where v is the speed as measured by some observer in some frame. So this solitary particle cannot have any potential energy. Alright. Now suppose there is an external agent that can do work on this object. I add an external agent. So this external agent does work on the object. And I will also assume that this rest mass energy is almost zero. Now if external work WE is done on this object, alright, and still there is nothing else in this universe that this particle can interact with, what will happen to its kinetic energy? It's going to increase. How much is it going to increase? The amount of work done. All of the work that is done on this object is going to increase its kinetic energy. So this change in kinetic energy, delta K, which is given by the final energy minus the initial energy, is equal to the external work done on the object. Okay? This is a famous principle in mechanics called the work energy relationship. Okay. Now suppose I have a box and I have this particle, my particle of interest. And along with this particle there is another particle inside this box. Now there are two particles. This could be one charge, this could be another charge. And there is the possibility of these particles interacting with one another. And how are they interacting if these particles were charges? By electric forces. Right? I don't want to say electrostatic because the particles can be moving, but through electric forces they are interacting. Now this interaction gives you the possibility of having potential energy. Okay? This potential energy has to be defined, however. Now this is my particle of interest. My eyes are glued onto this particle and I am observing this particle. And this is my system. Now if I look at this particle, it will have some kinetic energy, and the increase in its kinetic energy or the change in its kinetic energy. In physics, whenever we write delta K, it means conventionally final minus initial. This could be positive, negative. But the change in kinetic energy, once again, is equal to any external work done on this particle, which means there could be an external agent that does work on this particle, WE, right? But that's not the only force that this particle is subject to. Work is force times distance. So this particle can be under the influence of an external agent. That is, someone who's pushing this particle, imparting it velocity. An external agent. However, this particle is also talking to the yellow particle, which is inside the system. It's not external. So the presence of this particle inside the system also has the ability to do some kind of work on this object through the interaction. Interaction means there is some kind of force between these particles. So if that force acts over some distance over which this particle moves, it would imply work is being done on this white particle, on this white charge. Charges, by the way, are not colored. Someone asked me the question about whether charges are colored. Color is a complicated phenomenon. Objects don't have any color on their own. It's how objects interact with light that gives color. Gold can be yellow, it can be golden, but gold can also be red, gold can also be blue, depending upon the size of the gold nanoparticles. Okay, so gold itself doesn't have a color. It's how the object interacts with light that gives color. So charges are not colored. Anyway, so this particle that we're talking about is under the influence of this object, this charge that is internal to the system. So I can have work that is done externally, and I can also have work that is done internally through interactions. This int can stand for internal or it can stand for interactions. Alright? Now, this is external work, this is internal to the system, and this is the kinetic energy of a particle inside the system. Now if I take all the internal variables to one side of the equation and all the external variables to the other side, I will be left with delta K minus W int equals the external work done on the system. Okay? So here I have internal variables, and on the right hand side I have external variables. Now this object with the minus sign is defined as minus W int, negative of the work done by the internal forces, negative of the work done by the interactions that are local to the system. This is defined as the change in the potential energy of the system. Okay? So this means I can also write this equation in the following form. Delta K plus delta U is equal to the external work done on the object. Okay, just a minute. So if some external work is done on a system, it can increase the kinetic energy of the system, and it can also increase the potential energy of the system. Okay? Alright, you had a question.
This work is being done on the white particle, right?
Which one?
External work that we need. So then how it is affecting the whole system?
This work can also be done on the system. Right? When it's work done on the system, it will affect this particle as well, because this particle is a part of the system. Okay. So let's look at this equation. Delta K plus delta U is equal to the external work done on the system through some external agency. This external agency does work, it has the potential to increase the kinetic energy and the potential to change the potential energy and the kinetic energy, both of them. And this change in potential energy is defined as the negative of the work done by the internal forces, by other particles inside the system, and it comes with a negative sign. So let's look at an example so that I can clarify what's going on. I define a system. And my system is a capacitor with two parallel plates. And there is a charge on this plate, a positive charge, plus Q, and there is an equal magnitude of negative charge on this plate. Okay? You already know that there is electric field between the plates of the capacitor, and this is the direction of the electric field. Is there field outside the plates? No. These are infinitely sized sheets. Is this field uniform? Yes, it's uniform, and its magnitude is sigma over epsilon naught. Alright. Now this is my system. What does this system comprise? The system comprises a capacitor, and in electric terms it's just a uniform electric field. The capacitors make the electric field. These are the nuts and bolts to make the electric field, but the system is just the field. Okay? You can prepare this uniform field by other means as well. The plates are just the nuts and bolts, but the system is really the field. Okay? Now what happens is, there is a hole in one of the plates. I have a proton, a positively charged particle that is moving with a certain velocity v naught. It is prepared in a particle accelerator, it is accelerated, and it comes into this electric field. Okay, so it comes here with an initial velocity v naught. Now my system comprises the proton and the electric field. Now this proton is interacting with the electric field, or interacting with the charges that are on the plates of the capacitor. This electric field is internal to the system, and it can do work on the proton. The field itself can do work on the proton. Okay. Is there any agency external to this system? No. There is no external work that is being done on the system. So our equation that we've written here would become delta K plus delta U equals 0. Now first of all, let's look at what's going to happen physically without recourse to this equation. Let's forget about this equation. Let's erase it from our memory. भूल जाएं इसको. देखें फिजिकली क्या हो रहा है. ये प्रोटॉन अंदर आया, एक खास वेलोसिटी है इसकी v0. अब when it comes here, what's going to happen to the proton? A force acts on the proton. Previously it was moving with uniform velocity, it wasn't accelerating. As soon as it jumps into the system, it becomes a part of the system, it sees a force, an electric force. What's that force going to do? It's going to accelerate the proton. Okay? In what direction? To the right. Its velocity is going to increase from v0 to some value. Alright? If I would like to plot versus time the velocity of this object, of this proton, what will the graph look like? Parabola? Will it be a straight line or a parabola? What will be the shape of this curve? Okay, please plot this. This is something really simple. I would like you to plot this on your notebooks. सोचो, सोच के. Time 0 is when the proton enters the capacitor. नहीं. जीरो टाइम पे क्या स्पीड है? It's a really simple problem. You cannot study electricity and magnetism without knowing basic physics. Now, is this? लेकिन ये कर्व बिल्कुल स्ट्रेट लाइन है, ये क्यों विगल क्यों कर रहा है? क्या इस तरह है, क्या हो रहा है? जेन में क्या आ रहा है? सर इंक्रीज होगी. इंक्रीज होगी, कैसे इंक्रीज होगी? गुड. दिस इज इनकरेक्ट. How is it increasing? It must increase linearly. Why must it increase linearly? Because the acceleration is constant. The acceleration A is F over m. The mass of the proton is of course not changing. Is the force changing? Is the force changing? No, it's not. Why isn't the force changing? Because the electric field is not changing as we go from left to right. The electric field everywhere is sigma over epsilon naught, and you already told me that it's a uniform electric field. It's not changing. So everything here is constant. A is constant, which means that dV by dt is constant, which means that V must be a linear function of time. Okay? And this is V naught. So this is how the speed will increase. So if the speed is going to increase, can you plot a graph of how the kinetic energy is going to increase with time? Same होगा. Square होगा.
प्रोटॉन के एंटर होने से पहले, तो जब वो एंटर होगा तो इंटरेक्शन थोड़ी सी चेंज होगी, लाइंस ऑफ फोर्स भी चेंज होगी. तो सर फील्ड जैसे जैसे प्रोटॉन,
उसकी अपनी इलेक्ट्रिक फील्ड बहुत थोड़ी है.
प्रोटॉन की और सर जैसे जैसे वो प्लेट के करीब जाएगा सर वो कॉलम लॉ से सर
थोड़ी सी डिस्टॉर्ट होगी लेकिन नेग्लिजिबल होगी. प्रोटॉन है, याद रखो. 10⁻⁻⁹ गुल बहुत छोटा चार्ज है इस पे. All right. So the speed, the kinetic energy is going to change as a parabola. It's squared of this graph, right? So now I want to plot the kinetic energy on the same graph, but this is the velocity axis. So I make another axis here. I call it half mv squared axis. Okay? So at time 0 there is some velocity and the kinetic energy is half mv naught squared, and then it keeps on increasing, right? So this point is half mv naught squared. Okay, this green curve refers to this axis, this yellow curve refers to this axis. This is how you plot graphs, two graphs on top of one another. So the kinetic energy delta k is going up. Okay, but delta k plus delta u must equal 0. Okay, so if this goes up, what should happen to the potential energy of the system, of the proton? It must decrease correspondingly. Okay, so now if I were to plot with time, this is how the kinetic energy goes up, k. How should the potential energy curve look like? Like this? No, it should actually look like, right? So if this is my kinetic energy, it goes up like this. The potential energy goes down like this. So that the sum of, but remember, do you agree with me that this should be the graph?
Become less negative.
Not necessarily. The change in kinetic energy must equal the change in negative of the change in potential energy. So I need not make this negative. This could be anywhere, like this. It's just that the increase in the kinetic energy delta k must equal the decrease in the potential energy delta u, and both of them are in the opposite direction. So I don't have to plot this potential energy curve in this quadrant. It need not be negative. It's just the delta k, the change in kinetic energy, has to be equal to the negative of the change in the potential energy. Now this is something you can understand on your own. Delta k equals minus delta u. And let's look at what's happening physically. As the proton enters the parallel plate capacitor, it has some kinetic energy, half mv naught square, and it is accelerated towards the right. In layman terms, you would say that the negative charges are attracting the proton and the positive charges are repelling the proton. But these are layman terms. You would say this in your pre-ENM days. But now you're studying ENM, you would say that this proton is under the influence inside an electric field and work is being done on this proton. Who is doing the work? It's the field. The field does work, which means that the field has the capacity to do work. Okay, it means it must have some energy. Like a spring, you press a spring and leave it. The spring has the capacity to do work, and it can expand and flung, and it can make the object flee. So it has some energy stored in it. Likewise, the electric field is just like a rubber band. You compress it, it has energy stored in it, and it has the ability to do work. So this electric field is doing some work on this proton and its kinetic energy is increasing. And as its kinetic energy is going up in this fashion, as in the pink curve, its potential energy is correspondingly decreasing by the same amount. So its potential energy is maximum here and its minimum here. Here the kinetic energy is minimum and the potential energy is maximum here. Sorry, here the kinetic energy is minimum, potential energy is maximum. As the proton goes towards the negative charge, its potential energy decreases. It becomes more and more relaxed. Okay? So if I am standing on the ground, my potential energy is minimum. But if I jump, my potential energy goes up. I'm in an excited state. My relaxed state is when I'm closest to the surface of the earth. This proton likes to be close to negative charges. So when it's close to negative charges, its potential energy goes down, but at the expense of the kinetic energy, which has gone up. And this is the relationship. And we also know that this delta U is negative of the work done by the internal forces. So this delta Q is W internal. And what is the work done by the electric force? What is the work done? What's the work done? आप बताएं. What's the work done by the electric force here? वर्क की क्या डेफिनेशन होती है? सॉरी, हाँ, वर्क की डेफिनेशन क्या होती है? क्या होता है वर्क? कब होता है वर्क? फोर्स. ठीक है, क्या डेफिनेशन होगी वर्क की? फोर्स है, उसको किस चीज से मल्टीप्लाई करेंगे? डिस्टेंस, राइट? सो इफ the separation here is some x, okay, this work internal will simply be the dot product of F dx integrated from the initial position to the final position. Now the force is constant, it's just Q times E. And the angle between, remember this is a vector dx, the angle between force and the displacement is 0. So cosine of 0 is 1. I get a dx here and I get QEx. So this is positive, Q is positive, the electric field is positive, the magnitude x is positive, so delta K is positive. What about the internal work done by the electric field? It's positive. What about delta U? Is delta U positive or negative? It's negative. It's minus QEx. So as the proton moves from the left plate to the right plate, its potential energy decreases, whereas its kinetic energy goes up. And if I were to plot a graph between x, the distance moved, and the change in kinetic energy, and the kinetic energy, right, K, which is really kinetic initial plus delta K, I would get a straight line going up. And if I plot the potential energy, it's a straight line going down. And I can place this potential energy line anywhere I like. I can place it here, I can place it here, I can place it here. It's just that the slope of this line has to be the negative of the slope of the yellow line, because it's the change in potential energy which is equal to the change in kinetic energy. I can put the reference of my potential energy anywhere I like. Okay? ये जो मैंने ब्लू कर्व्स को ऊपर नीचे बनाया है, इसका ये मतलब है कि I can put my reference wherever I like. My initial potential energy